Okay, so what we have here today is a fluid dynamics question, typical HNC dynamics and machines module question. I'm going to go through a quick tutorial on how we would complete this. So the question says, an oil pipe tapers uniformly from 300 millimeters diameter at the bottom to 175 millimeters at the top. Oil flows from the bottom to the top and the pipe is positioned at an angle of 35 degrees and is 25 meters long. The pressure at the top of the pipe is 5 meganewtons per square meter with a flow rate of 1.2 meters cubed per second. Find the pressure at the bottom of the pipe, and it gives us there the relative oil density of 0.8. Okay, so what we have here is something like this. We have a pipe that tapers with 300 mil diameter here on this end and 175 millimeters at the top. We know that the pipe is 25 meters long and positioned at an angle of 35 degrees. 35 degrees. So for our calculations we need to know this height here. We'll call that h. That's a simple trigonometry. So our value of h is going to be equal to 25 sine 35, and that is equal to 14.34 meters. Okay, so we'll need that later on. Okay, so for this we're going to need two equations. We're going to need the continuity equation. Q is equal to A1 V1, which is equal to A2 V2. We're also going to need Bernoulli's. I use the form H1 plus P1 over rho G plus V1 squared over 2G is equal to H2 plus P2 over rho G plus V2 squared over 2G. Okay, so the continuity equation, it's saying that Q, our mass flow rate in meters cubed per second, is equal to the area of the inlet. The velocity of the inlet must be equal to the area of the outlet times by the velocity of the outlet. So the area there in meters squared and the velocity there in meters per second. That says that what you put in you must get out. You cannot, we are talking here about incompressible fluids, so therefore we put anything in here, it must come out the other end. Bernoulli's H1, this part here is our potential energy. This part here is our pressure energy. And this part here, the V squared, is our kinetic energy. Basically what Bernoulli's equation is saying that the sum of the potential, the pressure and the kinetic energy at one point in a fluid system must equal the potential, the pressure and the kinetic energy at another point in the system. Remember we said energy cannot be created nor destroyed, it can only be transferred. Okay, so with that basic, now let's pick some numbers out of the question. So we already have our value of h. Okay, so in this case it's going in, our fluid, our oil is going in at this end, coming out. So we're going to use the bottom as our datum, so h1 is going to be 0. H2 is our value we found earlier, 14.34 meters. We're also given a value of Q, a flow rate. It's in meters cubed per second, so that's handy. Q is 1.2 meters cubed per second. We're told the pressure at the top of the pipe, so that's P2, is 5 meganewtons per square meter, or 5 megapascals, which is 5 times 10 to the 6 pascals. Okay, so we've got the diameters at each end of the pipe, so we can work out the areas. If we work out these two areas, we can find the two velocities, which we need then to put into Bernoulli's. So using Q is equal to A1 V1. V1 is going to be equal to Q over A1. So A1 is going to be equal to pi d squared over 4, which in this case is going to be equal to 0.0707 meters squared. A2 is also going to be equal to pi d squared over 4. Using 175 mil, that gives us an area of A2 as 0.0241 meters squared. Okay, so we've got A1, we've got A2, we can find V1 and V2. So V1 is equal to Q over A1, which is equal to 1.2 over 0.0707, gives us an answer of 16.97 meters per second. Okay, just draw a line under that. And V2 using the same method is equal to 49.79. Let's see the point there. So V2 is equal to 49.79 meters per second. Now we can find Bernoulli's. So here we're trying to find P1. We know everything else. We know H1. We know rho. We've given the relative oil density. We know G. We know V1. We know G again. We know H2. We know P2. And we also know V2. So we're ready to go. So let's just write out the equation again. So we can refer to it. H1 plus P1 over rho G plus V1 squared over 2G is equal to H2 plus P2 over rho G plus V2 squared over 2G. Okay, so H1 is 0. P1 we're trying to find over rho G. Now relative oil density is 0.8, so that's 0.8 times 1000, which obviously gives us 800 times 9.81 plus V1 squared. V1 was 16.97 squared over 2 times 9.81, and that equals H2, which we know was 14.34 plus P2, which was 5 times 10 to the 6 over rho G. I'm going to use 800 this time, times 9.81 plus V2 squared, 49.79 squared over 2 times 9.81. Okay, so how I do this, I work out all the numbers rather than rearranging. I do all the numbers. I find that's easier when I'm teaching. So 800 times 9. With 0, we can forget about that. P1 over 7848 plus 14.678 is equal to 14.34 plus 637.1 plus 126.35. So what I've done there, this bit here is this bracket, this bit here is this bit here, and obviously this bit, and that bit there is that bit there. So I've just given all those a figure. Then it's as simple as adding these three up, minusing this one, times it by that, and that will give us a value of P1. So P1, do one more step just to make it clear, over 7448 is equal to 763.112, and that gives us a figure for the P1 is 5.99 megapascals. So we can see it's going in a value of at 5.99 megapascals. By the time we have the head loss, you only get it at the top at 5 megapascals. This tutorial here assumes there is no friction, no pipe friction. In an ideal world, this is an ideal scenario where there's no pipe friction. However, in real reality, that wouldn't happen. I hope this has cleared it up for you, been helpful. Look at my other videos for dynamics, mechanical engineering tutorials. Thanks.